Hey guys, Iris here. Welcome to another R demo video. And by the way, thank you very much for the response, for a nice response on the previous R demo, which I did about the box plots with statistical details and most classical tests like ANOVA, Kruskal-Wallis t-test, etc. So today I thought I would do something equally or even more practical, and particularly visualize results of different models. I picked up 16 different models and I already prepared the code, so we spent less time writing and you spent less time watching me write and spent more time learning. So in this video, what kind of models will we use? We'll get from the very simple linear model, either with one categorical predictor or with one numeric predictor. Then we go to the multiple models, of course, including not only linear model, but also logistic regression and multinomial model. And we will finish up with a very complex multiple mixed effects model, which are even non-linear. And at the end, I will give you some idea about the survival models and how to visualize them. It might be very long, so don't be surprised if I split this video in two. All right, why would we do this? First of all, because a picture is worth 1,000 words, and I wanted to do this video because it helps me on an everyday basis. I work with a lot of different people and a lot of different projects, and visualizing model not only helps me to quicker understand what the results are, but also to quickly explain what the model and the data are telling you, what the story is. And the goal in this video is to give you the minimum code, minimum amount of functions you can use for the maximum output. So another thing is I'll hide some bonuses in this video which would go beyond just model visualization because it belongs to these. One of these, as an example, would be checking assumptions and visualizing this. So it is worth to see the whole thing at least once. If you are here, I suggest you already know a lot about RStudio and packages and how to make models actually. So excuse if I will explain obvious stuff to you because some folks would be not as proficient as you. For example, before we use any function, for example, this glimpse function, we have to install the package which contains this function. And the package or the library is actually a collection of functions or collection of vocabulary which allows you to do some nice stuff. Before you use the library, we have to install the library. So every time you see the library and you don't have it, you get some kind of error message, you have to install it before. Sometimes installing one library would need to install another library, but the error message will tell you this particular package will be missing. So you install this particular package first, and then you install your library of interest second. All right. The library always have some goal, and this is Tidyverse is one of the best actually. It's a collection of different libraries, you see. These are all packages or libraries which are inside of this ensemble library. And we will use it for data wrangling, but it can do much more. Then we need some data to work with the data, and the package ISLR, which means Introduction to Statistical Learning in R, contains this data, wage data or salary data. If we run this package, we will have access to our data. What is this data? Let's have a quick glimpse into this data. We see that we have 3,000 observations and 11 columns. And we have variables like year, age. We have factor variables or categorical variables, education and job class. We will mostly use these. And of course, we have wage, which I like to see as a salary. So we can also manipulate some data, and this is a quick example to take less than 3,000 observations from the data. We just randomly select 1,000 observations of the data, but this random selection is supposed to be reproducible. and reproducibility is the main thing in science. So we have to set a seed to some number, you and me, it should be identical, in order to get exactly the same 1,000 random observations out of these 3,000 data. Okay, and the same seed grows the same tree. I have written it for myself, just as a reminder. So we take the wage data set, rename it as D because it's most convenient to write D all the time. Then, and this is the pipe operator you might have known from the tidyverse package, we select our 1,000 observations. Then we rename the variable wage to variable salary. And if we run this code and have a glimpse at our new data, we will have 1,000 observations, right? So without further ado, let's get into modeling and visualizing model results. Let's have a look what salary is doing depending on the job class. What is the job class? Let's have a look at the variable job class. And if we do this, we see that we have two different levels or two different categories. First of all, industrial workers and IT workers, like, I don't know, data science people or programming people. I really suggest you already know how to do linear models, but for those who doesn't, LM means linear model. That's all. And it only needs two arguments. The formula, you don't have to write it always, but you have to write the formula, and the LM function will recognize this argument. In our case, response variable is salary. That's what we're interested in. That's what we study. And the predictor or question variable, question, response, response, question. Predictor, which can predict salary, is the job class variable. And that's all for the formula. So the second and last argument we need is the data where these variables are coming from. So if we run this and then rerun the same model, you see, no error message, without explicitly stating these arguments, it will be the same. R will understand it. And in this way, the code is very handy. All right, so finally, let's get to the visualization. Of course, we have to plot it somehow, and the cool functions, cool plot visualizations come from cool packages, and one of those is effects. Remember, in order to use some functions, for example this, we have to load the library first. If we don't have the library, we have to install it first. So I have this library, nice, and if we just use our model, which we just created and saved in the object M, and say plot all effects of this model, despite the fact that we have only one effect job class, following will be there. We will immediately see that people in the IT area earn more than people in the industrial area, just like that, really quickly. I find it really interesting and intuitive, much more than looking at the estimates and numbers. It's okay if you understand what you're doing, but it can be really frustrating if you're a beginner in modeling. This is much better for communication and for understanding, or for a quick exploration of your dataset. Good. We're done with the first model. Let's get to the numeric predictor and also use a simple linear model. We have a data, we have numeric predictor, and we have salary, which will answer the question how age influences the salary. Let's run the model. No error message, nice. And let's use already known function plot all effects M. If we plot it, we see that all we need to earn more money is just to get older. So stop learning, stop developing your career. You just need to be older in order to get more money. That's what this plot is saying. All right, since we already knew this function, let's learn one more thing. If we do grid true, we can also write true. It's the same thing. We will get the grid, and sometimes it's handy to to get some idea about exactly the age you want to estimate the salary from. So grid sometimes helps visually. So let's get to a bit more complicated model. Now we have multiple linear model with two categorical predictors. Job class we already know, the industrial people and information technology people. What is education? Education, let's have a look at this. We have 5 levels of education, not even a high school, some college, and advanced degree, most probably some PhD. And if we want to know how education influences salary, we just add this variable to the model with a plus. All right. If we run the model, we have the results of our multiple linear model in the object M. And if we use already known function, we will appreciate the all effect name of the function. So, you don't have to plot every individual effect. You can plot all of them at once, and you could not make it as easier than that. I really love it. I use it every day, and that's why I try to share it with you. All right, what do we see here? IT people still earn much more than the industrial people, and you see that the higher the education, the more salary you get. It's kind of obvious because you know more, you can offer more to the world. But sometimes some paper or your boss or even you want to have only one plot and get rid of the other because it's not significant or whatever. And in order to plot effect of only one predictor, there is a function in the same package we already loaded, predictor effect. And all we need to do is to specify the predictor in the model M. It's kind of intuitive, isn't it? And if we plot this, if we execute this function, we will have only one plot of only one predictor from the same model. The other predictor is still there if you need it. For example, you can have a look at this. It's still there, but we have only one plot we needed. Right, we're ready at the multiple linear models. Let's get multiple linear models with numeric predictors. We have age. We already saw that we only need to get older in order to get more money. And year. Interesting. Let's see what the model will tell us. Again, after running the model, as easy as that, we have two predictors. They both influence our salary, and they are wrapped up in the linear model function which produces an object. If we plot it, we also get all effects, in this case 2 effects, for our model. Again, the age didn't change. What is with year? Interestingly, all we need to do is just to be alive, because the laws of economy need economy to grow. So you see, with the time, even if we don't do anything, the salary will grow, apparently, if we believe this data. All right, so sometimes it is useful to display the confidence intervals in a different way to, just to compare some parts of the age or some years. And there is an argument, confidence intervals, in our function all effects. And we can change the style of these confidence intervals from the lines, which you see here, to the bars. And if we execute this function, we can immediately compare the salary of the year 50 and the salary of the year 60. Most probably this will be significantly different because they do not overlap. Well, the visualization of results is the main interesting thing in this video and in your data, but sometimes you want to visualize these estimates, and instead of having reported this strange looking table and explain it to people, it's much easier and much more intuitive to visualize even this and sometimes even the significance here. For this, we have a plot model function. Yeah, as easy as that. Plot model, and we already have our model, which is M. Of course, this function has to be loaded from the library sjplot, and sjplot is an amazing library from an amazing researcher and programmer, which I really respect. And you can always have a look who it is if you're interested, because this guy has more to offer. He has more packages. So if we have a citation, you know that it is Daniel Ludecker, and he produced several really, really amazing packages. All right, so we load this package and we ask it to plot the model. And here we go. Here are our results. These both predictors are significant. We see it here, and they do not cross the zero. So if the confidence intervals of the predictor do not cross zero, the predictor is most likely significant. That's what these numbers are telling you. That's what p-value is telling you, and that's what not zero crossing confidence intervals telling you. All right. So enough for this. Let's get to another model. Now we have multiple linear model with both numeric and categorical predictors. We already know age. You need to be older to get more salary. You already know education. You need to be more educated in order to get more salary. But can we plot them together? Well, yes. Again, using only this universal function, plot all effects, we can get our results. However, sometimes the results are cramped and we want to display differently, not in 2 columns in 1 row, but instead in 1 column in 2 rows. And of course, this function provides these arguments, rows and columns. And if we execute this, we will get our wishful results. Looks much nicer, isn't it? Now we come to the first bonus. We have to always actually check the model assumptions before we do the model, because all we did until now are the linear models. And there are some ways to deal with this. If you do model, you always have to check an assumption. Or several assumptions: linearity, multicollinearity, normality of residuals, etc., and influential points. And the older ways were always kind of, I don't know, less elegant, I would say. And there is another way, I think the better way to check the model assumptions, and it calls actually check model. Of course, it's part of some library, and this is the library. You can have a look at the citation of this library to figure out who is creating these libraries. And if we check the model assumptions only with using check model function, all we can get is actually checking all the assumptions in one plot immediately. How amazing is that? First of all, we see the check for multicollinearity with the variation inflation index. If you don't know what it is, you will, just believe me. And the correlation between these predictors is very low, which is good. Usually, if the variation inflation factor is below 5 or below 10 or below 20 for the interactions, then we are good to go. These assumptions for multicollinearity is checked. The normality of predictors, it looks like they are kind of normally distributed because the predictors produce kind of the bell curve. But if you look at the quantile plot, which is already there by default, after using check model function, we see that they are not really normally distributed. And we see why, because there are some people who earn a lot, and these people do skew the residuals. The point of this is that you can check all the assumptions using only one word, actually, only one function. It could not be easier than that, and I really love it. So let's go further and progress to the linear models with interactions. The interactions differ from the normal linear model simply by this small sign. Instead of the plus in the model, we use multiplication sign. That's all. What does it do? If it would be the plus, we would check the influence of the education on the salary, and we would check the effect of job class on the salary. However, using the multiplication and having this interaction between the two predictors will allow us to check the influence of education, of every level of education, in every level of job class for the salary. For example, let's just make a table of the education and job class, and we see that we have several people in the crossing of these two variables, and we will get the effects for them for example, the advanced degree people in the industrial sector, and they will be compared to the information technology people with the advanced degree. So, all right, if we run this model, we will create our object. And again, the beauty of this function all effect, the more I use it, the more I love it, is that it simply does work and plot everything. Now, the model knows that this interaction show you this in this way by displaying the formula, and it shows you by connecting these plots. They are kind of connected. They are two subplots of the same plot. They are not separated anymore like in the previous examples. So we see this interaction. And since we already know this amazing function, we can learn something new to it. For example, we can put all these lines on one single plot. We just need to use multi-line argument in these strange listed lines. But if we use it, we will get two job classes and estimated salaries for every category in job classes on the same plot. Isn't it beautiful? I love it. Yeah, but the confidence intervals are gone, so we can replot it. We again use only all effects, which we already used. We again use this argument, which we already used, and we already know about confidence intervals. You remember in the previous example, we used bars as an example, but here we use auto, and it will automatically display bars because it makes sense for the categories. So I told you that we can check the difference between these, and that's actually what you want to do if you make complex models. You want to know whether this salary is significantly different from this salary, or this salary is significantly different from this salary. And you might have known that this is a post-hoc analysis. You already have your model, you already have your estimated salaries for every group, and now we have to pairwisely compare them. Well, now we get to the bonus number 2, easy post-hoc. I call it easy post-hoc because in one single line of code, you can check pretty much everything. Let me show you what I mean. So again, we need a function for this. This function is hidden behind this amazing package amins. And if you wonder what amins is, you always can ask R. So the estimated marginal means of the least squared regression, and we have a least square regression. So if we want to pairwisely compare the job classes for every education level, we have to use this vertical slash, and if we execute this, we will get 5 different tests. We have 5 tests because we have 5 education levels, and for every education level we will compare the job class industrial to job class information technology and get p-value for this. If we have a look at the plot, we see that there is no significant difference between people who didn't even finish the high school. It doesn't matter in which area they work, industrial or information area, they will not get differently more money or differently less. And if we go to the last part, we will see that the results are significantly different, namely that IT guys earn significantly more than the industrial guys. We just did 5 tests just like that, but what if we want to compare all the information technology guys to each other? We see that people in the area of IT with advanced degree earn significantly more than all of them. But if some journal or your boss or yourself want to have these p-values, we can do the same, but just change the order of our variables. So we do this bar and execute, and suddenly for every class, we just talked about information technology class, that's what we have here, we compare every of the education level to every other level. Isn't it amazing? Just like that. Moreover, we can go one step further and just remove it and write a simple formula we just have written to the argument of a means, to the function of a means. So remember, it's just our formula. And if we pairwisely compare every education level or every category independent on the job class to each other, we will get 45 tests just like that from one single line of code. Isn't it amazing? And of course, just a small reminder, if you do a lot of tests, you have to adjust p-value because you increase the probability to discover something false. It actually calls false discovery rate. That's why we have to adjust the p-value with the, I like it, false discovery rate, but there are several methods. Most famous is Bonferroni, but I personally don't really like it. Bonferroni is too conservative in my opinion. That's why I use FDR or Holm method. All right, that was the second bonus. I hope you find it useful. So let's get to the next model. We have multiple linear model with interactions of a numeric predictor. So we already know age, we already know, we don't know health. Let's have a look at the health. What is our health variable? Health variable has two levels, the good or below good health and very good health. Interesting. Does salary have an effect, or does health and age has an effect on salary? That's what this model can to help us figure out. Again, we use my favorite function, plot all effects m, and we'll get our results. We also already know how to put two lines on the same plot. Let's execute this, and we will get this beautiful plot, which will tell us the story, namely that people with a very good health earn more. And I would guess significantly more because the confidence intervals do not overlap with the other health statement. So you remember our plot model where we plotted the coefficients? So we also can use it here, but let's add something new to it. Interestingly, this function plot model can be as useful as all effects function, particularly if we specify different type of modeling we want to display. We say we need interactions, then we will get exactly the same plot as we did with the all effects function. You can plot it separately by using other argument by the type, but it's not the point here. Look how easy is it just to plot very complex model. The advantage of a plot model towards the all effects function is that we can use the ggplot2 arguments with it. So ggplot2 is the most famous visualization library across the languages in my opinion. It's even better, I think, than a lot of famous Python libraries. You might hate me for that, but it's really just my opinion. And that's why we can use the arguments of ggplot, for example, to change the appearance of this plot with the plot model. For example, if we don't want this legend to be here, but want it on the top, we also can add the arguments which we know from the ggplot2 legend position, and we put it on top. If you don't know ggplot2, it's okay. You have the code here. And we can even change some arguments like changing what we are measuring, something different. We just can write something different on the axis. Cool. So we already have some kind of complex model. We have still linear model. We have two predictors with interactions, and we forgot to check the model. Now and then we have to do this. And if we use already known function check model, and look at the results, we will see the same story. There are non-normally distributed residuals. And as I told you, the correlation in interactions model, like here, it will be there. It's normal because health is part of this argument. They will be correlated and highly correlated. But if the correlation is below 20, for interactions, it's still kind of acceptable. But we have to fix this problem. So the check model function allows us to see that we have a problem. Maybe this model is not really linear and we still use linear model. You see, we use LM, our argument, which just produces least squared linear model. And sometimes I only plot quick models without modeling anything explicitly. And again, ggplot2 package, which I just told you about allows you to do this. For example, if we take our data D and use age and salary and plot him, we will see that this is not really linear. There is a way, really nice way and easy way to check whether there is a linear relationship on the fly by using geom_smooth function. Only by typing this, you will get the model results of a nonlinear model because the data will be just fit. Isn't it amazing? It even tells you what kind of model it was using. It used the GAN model, generalized additive model, with the smoothing factor. It couldn't be simpler as that, but we can go one step further and create two models in the same plot. For example, we have to say tilde health, because the health is what we still miss. And suddenly we will create two nonlinear models for good or less than good health and for a very good health. Isn't it amazing? As quickly as that, with this simple code, you created two models and will check the assumptions whether the data are linear, whether the relationship between these two variables is linear. We see it's not. But it can go even further. If we check the job classes, suddenly we can create 4 models just by using this simple code. And of course, you can create more and more. So if you get the idea how it works, you can check your data, have a look at your data pretty quickly. It allows you to get intuition before even get to modeling. So, in this part of the video, we handled linear models or least squares models. Particularly, we looked at the visualization of the categorical predictors, numeric predictors, multiple linear regression where both types of predictors are combined, and even visualization of the interactions. And I think it's a good time to split the video in half because it's became pretty long. And since we go into the different kind of modeling, I would like to split this video here, and in the very next part of this video, I will show you how to visualize nonlinear models, logistic regression with interactions, mixed effects models with interactions, and even mixed effect models which are nonlinear. Moreover, we will go to the visualization of the multinomial regression, which was done by the means of the neural network. And finally, we will finish up with the visualization of the survival models, particularly Kaplan-Meier curve, exponential parametric models, and Cox proportional hazard models. Since in this video we introduced all the necessary functions and concepts like plot model, plot all effects function, we saw how to check for the assumptions, the next video will be quicker and even more informative, so stay tuned. And of course, if you like this video and found some value, consider to like and subscribe, and as always, thanks for learning.